Good evening, everybody, and welcome to this public talk, which is part of a week-long series of events being run as part of uh, virtual Pompey Stargazing 2021, which is hosted by the Institute of Cosmology and Gravitation at the University of Portsmouth. My name is Dr. Nick Bond, and I'm going to be the host for this public talk this evening. So before we get going, I just want to introduce our speaker for this evening. So our speaker is Professor David Wands. He's a professor of cosmology, and he researches the very early universe and the origin of structure. He studied at the universities of Cambridge and then at Sussex before joining Portsmouth. When he joined, he was a Royal Society University Research Fellow, and then he became a professor, and he's actually been the director of the Institute of Cosmology and Gravitation from 2010 through to 2020. He is, of course, as you may have guessed, quite interested in physics, but he also likes football and fuzzy animals, and maybe he'll talk a little bit about that during his presentation. Who knows? So I'd just like to pass over now to David, and he's going to talk to you about some really, really interesting cosmology.
Okay, thank you, Nick. I'm delighted to speak to everyone online for this virtual Pompey Stargazing event. I've been working in Portsmouth for more than 20 years now, and as a cosmologist, I'm interested in studying the universe really on the largest scale. So I'm going to like to tell you a bit about that and how we apply science and physics in particular to our universe. So there are three ideas that I'd like to convince you of by the end of the talk. So I'd like to convince you that the universe is big, very big, and I hope I'll succeed in that much at least. I'd like to show you that there's structure in the universe, even on the largest scales. When we're exploring and building maps of the universe, we see structures on all the scales in our universe. And then my third challenge is to persuade you that maybe all of the structure and wonder of the universe that we see could actually come from nothing, from empty space. So let me start with this beautiful image, which it's produced by an artist, Pablo Carlos Badassi. But he did it in conversation with scientists, with cosmologists and astronomers from Princeton University. And it's particularly inspired by astronomical data of maps of our universe from the Sloan Digital Sky Survey that I'll tell you more about later. And it's a map where, if I actually set myself up with a laser pointer to show you here with the red dot, you can see a map of the universe that we see around us. So at the center of this is, of course, our sun, you see, and this small blue planet orbiting the sun, the Earth. And what the artist has done here is an artistic representation of the whole observable universe. But to show the details on the small scale of our solar system and our planet, as well as the scale of the stars and the galaxies. It's based on a logarithmic map of the universe. And that logarithmic map means that every time you move out into each successive shell, the scale of the map changes by a factor of 10, so that increasingly, as you move out, you're seeing larger and larger scales in our universe.
David, I'm so sorry to interrupt, but I think we've had a technical hiccup and your slides aren't popping up on the YouTube feed.
I need to actually share some slides with you rather than just talk at you.
Apologies.
So let me show you, because I've got a nice, beautiful picture I'm talking about. Okay, along with my Zoom link. Okay, so I hope you can see that now, Nick. The image of our entire observable universe from the artist Pablo Carlos Badassi. Right, so this is, here we go. This is Yeah, this is us at the center of our observable universe. And this shows an image as we look out into our universe from our solar system. So you can see right at the center our sun and our planet Earth orbiting the sun at the center here. And this is a artistic representation based on a logarithmic scale, our universe in a logarithmic scale. So every time you move out to a successive shell, further and further distance out from the center, the scale of the map is changing. And so the scales become 10 times larger as you move out towards the edge, until by the time you come to the edge, you're looking at the largest observable scales in our universe. And to try and convey just how big the observable universe is, it's useful to think maybe in terms of the travel time for light in the universe. The speed of light is a fundamental constant. Light travels at 300 million meters per second, 300,000 kilometers every second through our universe. So it's the travel time of light is a good way to describe the distances in our universe. And as we look out into our universe, because of that finite travel time speed of light, you're looking further out, you're looking further back into the universe. You're seeing the universe as it was in the past when that light was emitted. So within our solar system, for example, if you think about a planet which you can see on the map here, such as Jupiter, Jupiter's about 900 million kilometers away from us, a huge number of kilometers. But if we reduce that we can think of that in terms of the time it takes light to travel to us from Jupiter. It takes about 40 minutes or so. So by the time we get to the end of my talk, someone in Jupiter would just be able to see for the first time the light from the Earth when I started my talk. If you go further out into the cosmos, the next landmark you might think about is the distance not to our sun, but to the nearest star other than the sun. It takes about 4 years for light to come from the nearest star. So there's a huge jump in scale from the planets, which are light minutes away, to the nearest stars that are years away. And if you then consider the scale of our galaxy, so our galaxy is made up of hundreds of thousands of millions of stars, so many stars that they form a Milky Way across the night sky. If you're lucky enough to be away from the street lights and a dark, clear night, the Milky Way stretches across the night sky. That is our galaxy, hundreds of thousands of millions of stars. And then it takes, if you go to the center of our galaxy, it takes tens of thousands of years for light to travel to us from distant parts of our galaxy. So we're beginning to build up a scale of the galaxy, but each galaxy itself becomes just a dot in the large-scale structure of the universe that we see with the latest astronomical surveys. They map out the distribution of galaxies, and that's what forms the cosmic web that you see here at the edge of the observable universe. These distant galaxies are billions of light years away. So the light we see from these galaxies tells us about the universe as it was billions of years ago. And as we'll see, they form they're not uniformly distributed, but they're built into a cosmic web of structures in the universe on this very large scale. So, as to quote the words of Douglas Adams, the space is big. It's really big. So, and you can gain a concept of that from just the time it takes light that travels at 300 million meters per second, just how long it takes billions of years to travel across our universe. to bring things back maybe to a slightly smaller scale, I'd like to introduce you to some of the people who study the universe. In Portsmouth, we have an Institute of Cosmology and Gravitation at the university, and we really specialize in studying the universe on the large scale and answering, therefore, some of the big questions associated with the origin and the evolution of our universe. So we have about 60 or 70 researchers in Portsmouth come from all over the world to work with us. I think that at the latest count, we have about 17 different nationalities of people working in Portsmouth. Usually, on a January night, we hold a stargazing event down at the historic dockyard in Portsmouth. So the institute here is about half a mile from the Portsmouth Historic Dockyard, where on a dark January evening, we're usually running these stargazing events in person, face to face. This year, we're doing it online. So some of you may be joining from far away and don't know much about Portsmouth. Well, it's Britain's only island city here on the south coast of England, and our institutes and the university are here just half a mile from the seafront. So half a mile, that's about a couple of microseconds for light to travel from the university to the seafront. So the universe, as we've seen, we're looking out billions of years. And one of the biggest maps is constructed by the Sloan Digital Sky Survey of the universe. And that's a survey which researchers in Portsmouth have been involved in for the past almost 20 years, building up what remains one of the largest maps of the distribution of galaxies in our universe. So here you see a selection of just some of those galaxies mapped out on a scale of billions of light years here. So each dot in this map, each single dot is a galaxy, and remember, each galaxy is hundreds of thousands of millions of stars. And you see that distinctive web and filaments and clusters of galaxies gathered across the sky. And this map is made not from Portsmouth, sadly, because our skies are too cloudy most of the time, but from a telescope in New Mexico, which makes dedicated surveys of the sky and created the first large-scale digital survey of all the galaxies in the sky. So it's built up the positions on the sky of millions of galaxies, and indeed, if you go to the Galaxy Zoo website, you can see some of the individual images that are taken, that individual galaxies that make up this map of the universe. So we can ask how far back we could actually look. Could we really look back to see the Big Bang itself? Is there any limit to how far back we can see in our universe? And sadly, we're limited as to how far we can see. It's a bit like if you look up at the sky in Portsmouth, you might not see very far at all. You might not see the stars because often it's cloudy. And if you've got a cloudy sky, you only see to the surface of the cloud. The cloud above us, if on a cloudy day, you basically see through the transparent air, but then you're limited by the surface of the water vapor in the clouds. The water vapor in the clouds are opaque, and we can no longer see through that. So when you look up, you see as far as that surface, opaque surface of the cloud. And there's a similar phenomenon in our universe, where if you think of us looking out into the universe, looking back in time, we're looking back to a time when the universe was smaller and younger, smaller, denser and hotter. And there comes a point when the universe becomes so dense and hot that it reaches a temperature where atoms are ionized into charged electrons and nuclei. And at that point, it becomes an opaque plasma. And that's called the surface of last scattering. And so we see light from this time 14 billion years ago. So we're looking out 14 billion years into the universe. We see the universe as it was just 400,000 years or so after the Big Bang. And that's a surface of last scattering. But we use physics to understand the universe, even at that early time. In fact, the temperature it's hot, it's several thousand degrees, but it's familiar physics of, for physicists, we're studying a plasma of charged particles, typically hydrogen atoms, protons, light electrons, negatively charged particles, and light. These wiggly particles here I'm indicating here are the photons of light that in the hot plasma scatter off the electrons and protons. So this is well understood scattering of light off charged particles. And also we know that once the energy drops below a critical temperature of about a few thousand degrees, those electrons and protons can combine into neutral atoms, most of the atoms being hydrogen atoms in our universe, and they're neutral, and so light actually can free stream past these neutral atoms. It doesn't scatter off because they're not electrically charged. The photons can free stream, and the universe becomes transparent. So we see light from this surface, the surface of recombination of the electrons and protons. And we understand that through atomic physics at these early times in our universe. But it describes well the pattern of light that we expect to see, and then we can compare that against observations. And in this case, the first observations were made back in the 1960s by two radio astronomers, Penzias and Wilson, at Bell Labs in New Jersey. They were allowed to play with this giant radio telescope here, and they pointed it up at the sky to see what they could see, if they could see sources in the sky. And what they found was, in every direction in the sky, a uniform, smooth background radiation. And they didn't know what it was, but they actually picked up the phone and talked to the physicists in Princeton University, just along the road in New Jersey. And the physicists in Princeton were actually building a telescope to go and detect what they thought would be there, radiation from the hot Big Bang. And so this is one of the cornerstones of the hot Big Bang model, the discovery, first of all, of this radiation, this light from the edge of our universe. And it's a thermal radiation left over from the hot plasma of the hot Big Bang. So it comes from that last scattering of the light 14 billion years ago, and it shows us the universe as it was 14 billion years ago. Now it's a faint, feeble radiation permeating through all of space, just 3 degrees above absolute zero. But crucially, it's evidence of the way the universe, the hot early universe. And indeed, it's a topic of, continues to be a topic of intense study for cosmologists. The state of the art, these images from the European Space Agency Planck satellite, images you can see at different frequencies here, 9 different frequencies. They built up a map of the sky and these different frequencies. You actually see a broad band of light. This is the Milky Way, our galaxy, emitting in the radio frequencies. But away from the galaxy, you see the thermal radiation from the hot Big Bang. And when you combine these images to pull out the thermal radiation, there's this exquisitely detailed image of the light which comes from the distant universe, from the edge of our observable universe. It's 3 degrees Kelvin in all directions. It's very uniform, but what's plotted here are the small variations in temperature, just 1 part in 100,000 hot and cold spots across the across the sky to about 1 degree on our sky. And so again, even in that light from the most distant light in the universe, we see these structures. They look small here, but they become on the edge of our universe. These are actually billions of light years across these structures. So for the final part, second half of my talk, really, I'd like to tell you about where we think all of this comes from. Where does all the stuff in the universe come from? It's a bit like looking up in my dad's attic and thinking, where does all this stuff come from? Well, when we look out in the universe, we see particles, we see stars and galaxies, we see energy, and as I say, we also see structures on all the scales in the universe. So to answer that sort of question, we need a theory not just of matter, but a theory of space and time itself. And the theory we use is Einstein's theory of gravity, general relativity. So this is a mugshot of Einstein. And he had this amazing insight to realize that gravity is really a manifestation of the curvature of space-time. And so there's a simple sort of description of Einstein's theory of general relativity encapsulated in these two sentences here. First of all, it's the curvature of space-time. Gravity is nothing but the curvature of space-time that tells matter how to move. So we think there's a force of gravity pulling on us, but Einstein's realized that this was really just us moving in a curved space-time. So that's the first great insight that he had. But the second sort of complementary aspect of general relativity is that although space-time tells matter how to move, it's matter that tells space-time how to curve. So the curvature of space-time that we feel is actually caused by the matter that's moving in the space-time. So it's this elegant but at times complex mathematical description of space and time and energy. But it's exactly the theory we need to use to describe our universe. And it was soon discovered after Einstein proposed the theory that in fact our universe is a dynamic, the space and time in our universe is a dynamical quantity. And in fact, we have an expanding universe. And those equations were first discovered by this man, Alexander Friedmann, the Russian mathematician and meteorologist, who came up with one of the first solutions of Einstein's equations. And we realize now that his solution was describing an expansion of space driven by the matter, the energy density in space. And so that's how matter determines the curvature of space-time. It's the matter that determines the expansion rate of space. But also, as the space expands, the matter itself, the density of particles, is diluted by the expansion. So the conclusion is that although matter can drive the expansion of space, the density of matter is rapidly diluted by that expansion. And so the expansion slows down. And there realized there was a puzzle as to why the universe expansion continued for so long. Why is it that the universe gets so big? Or equivalently, why is it so old? Why does that expansion last so long? And the answer to that, what's now probably the most widely accepted answer to that, comes from a theory called cosmic inflation. And this is the bold suggestion that actually all the expansion and all the matter, and indeed, as we'll see, all the structure that we see in the universe actually comes from empty space. So empty space, you might indeed think of outer space far from planet Earth as being a good example of empty space. But even in our solar system, there are particles. There's even, if nothing else, the photons of the cosmic microwave background radiation. Even in empty space, there's some low density of particles. So the true vacuum, the real empty space, is what's left once all the particles are taken out. And you might think that there's nothing much more can be left once there's no particles. Surely there's no physics. There's nothing of interest in empty space. But certainly, there's no pressure waves, for example. So the reason you can hear my voice is because of the gas particles, the molecules in this room, communicating the waves of pressure as I speak to the microphone. But in empty space, there is no sound because there are no particles, or it's too low a density of particles. So in vacuum, there's no sound, no pressure waves. You can't hear the Big Bang. But what there is, and there can be, is fields. So which play an important role in physical theories. And where there are fields, there can be energy. So let me give you an example of a field that might exist in empty space. For instance, even far from the Earth's surface, the Earth's magnetic field connects the North Pole, the magnetic South Pole, and the magnetic North Pole of the Earth. The Earth is a magnet, and field lines extend out into space from the Earth. It extends out into empty space. So you can have magnetic fields, you can have electric fields in vacuum. You can, of course, have gravitational fields in vacuum. So the moon feels the curvature of space-time, so the pull of the Earth, even though it's in almost empty space. So even though you have no particles, you can still have fields. And the particles and fields are closely linked. Photons, for example, particles of light, are ripples in the electromagnetic field. In recent years, we've discovered gravitational waves, and those are ripples in space-time itself. Those were discovered and seen for the first time in 2015 by gravitational wave detectors, the LIGO detectors in the US. And now in Portsmouth, we've got a team of gravitational wave scientists who are seeing these signals of gravitational waves from the distant universe. They're produced, these ripples in space-time are produced by orbiting and then merging black holes, violent events in space-time. My colleague Laura Nuttall is going to be talking about that in a talk later this week. And you might also have heard of the Higgs field, or rather you might have heard of the Higgs particle. The most recently discovered particle in physics, fundamental particle, is actually an excitation, a ripple in the Higgs field. So although indeed in the room where I am and the room where you are, I bet there are no Higgs particles. It takes a lot of energy to produce a Higgs particle, but nonetheless there is a Higgs field in the room with us. It's uniform and it's undisturbed, but if you could put enough energy into it, you could that Higgs field could describe the excitations of that Higgs field would be a Higgs particle. And the implications of fields in the very early universe was realized by, well, these two physicists, cosmologists, I should say. In the 1980s, this began to be taken seriously in models of the early universe. So on the left here, I've got a picture of and another sort of schematic of our universe where time runs upwards. So the present day is up here, 14 billion years after the Big Bang. The temperature is 3 Kelvin, that's 3 degrees above absolute zero. And as we run back in the past, we see that surface of last scattering of the cosmic microwave background photons 400,000 years after the Big Bang. But if you run the history of the universe backwards, you get a smaller, denser, hotter universe at higher and higher temperatures. And the sort of temperatures explored, for instance, in the Large Hadron Collider in CERN, those sorts of temperatures are realized something like a millionth of a second after the Big Bang. We reach those temperatures. And in even higher temperatures, physicists believe that all the forces of fundamental forces would become unified. For instance, the strong and weak nuclear forces, as well as electromagnetism, could be unified at even at fantastically early times, a fraction of a second after the Big Bang. This is, yes, I've put the temperature here, something like 10 to the 27 degrees. That means something like a billion degrees, far higher than any energy scale you could reach on Earth. And at that time, the universe is so small, so dense, that our entire observable universe could be as small as a centimeter across. And the theory of inflation was the idea that fields at that time existing in empty space could drive the expansion of the universe. And Alan Guth proposed this. He was a researcher at MIT in Boston. And in 1980, he proposed the grand unification of forces could give rise to a high energy density of fields, but no particles, just fields in the early universe that could drive this rapid expansion. It attracted a great deal of attention in the US, but in fact, also at the same time in Russia, cosmologists were exploring similar ideas, and they actually pointed out that the previous year, Alexei Starobinsky here had proposed a similar model for the rapid expansion of the very early universe. In his case, he was considering a modification of gravity. And but on either side of the Iron Curtain in 1980 and 1981, the idea of inflation, cosmic inflation, was beginning to take hold. And this was exactly the idea of inflation driven by empty space. And the idea here is that you can have space that is empty, where you've taken all the particles out, there's nothing left in your box here, and yet the crucial difference here that plays a role in the expansion of space is that it can still have an energy density, that even empty space can have an energy density determined by the presence of fields rather than particles. But the trick here of having empty space drive the expansion of the universe is that it has an energy density, it can drive the expansion according to Friedman's equations, but because there are no particles, once you expand the universe, you still have no particles, you're still in the vacuum, so whatever the energy density you have as the universe expands, it remains the same with the expansion. And that's what can give a runaway expansion rate in the universe. That might sound really strange, and it did sound strange to a lot of scientists at the time, and many were very skeptical about this idea that the expansion of space could be dominated by empty space. But in the intervening years, we've seen that actually the universe today exhibits very much this kind of expansion, and that's what we call dark energy in the late-time universe today. So there's evidence that the universe can actually expand like this. If you do have an expansion that's driven by an energy density that doesn't decrease with the expansion, then the expansion rate is constant. And mathematically, a function whose, as drawn here, a function whose rate of increase is proportional to the function, well, as the size of the universe grows in this case, the rate of growth keeps growing, and you get a runaway or exponential expansion. So you get an exponentially growing universe. As I say, the density remains constant. The actual size of the universe is constantly increasing. So the total energy in the universe is exponentially increasing. So it's been said that the universe itself is the ultimate free lunch. Out of nothing, you get expansion, continued expansion. until in these models, it's necessary to have some instability in the force vacuum that causes it to decay, because the hot Big Bang, the particles that we see in the universe today, must come from somewhere, and the idea is they come from the energy of this what we call a false vacuum, the positive energy of the vacuum, as it decays into the true vacuum of almost zero energy density that we see in the universe today. But the energy of the high energy of the very early universe vacuum would be released into energetic particles, and that would be the beginning of the hot Big Bang model that we see describes the light, for instance, from the cosmic microwave background radiation. Okay, so this is a big, bold idea about the very distant universe beyond that last scattering surface. So we can't see light directly from this inflation era. But the reason it's taken seriously by many cosmologists is because there's an unexpected bonus that feature here, that apart from this fantastic expansion of space, within the model, there turned out to be an unexpected extra when you consider quantum physics at work. And that's because in a quantum theory, there are always fluctuations. And as we'll see, that's what gives us structure in the universe. So having said in empty space, there's no particles, just energy or fields. If you think about what happens in quantum physics in empty space, what we're saying is there's no real particles. There are no real Higgs particles in this room right now, but there are virtual particles. In the quantum theory, the quantum uncertainty means that there are virtual particles that fleet in and out of existence in accordance with the Heisenberg's uncertainty principle. So there are no particles that survive no Higgs particles, long-lived Higgs particles in this room, but there are quantum fluctuations in the Higgs field, for example, that you can think of as virtual particles. And the implications of that in gravity had been studied in the 1970s by none other than Stephen Hawking here, not Marilyn Monroe, as far as I know, studying quantum mechanics in gravity, but Stephen Hawking here at, I think this is his 60th birthday party. He studied quantum fluctuations around a black hole event horizon, and realized that in this gravitational background in general relativity, combined with quantum fluctuations, you could get Hawking radiation. That is, black holes radiate, and so there are fluctuations seen outside a black hole from these quantum effects. And soon after inflation was proposed, Girth and Hawking and others, and Starobinsky and others, realized that there's a similar effect, an analogous effect in an inflating universe where there's a cosmological event horizon, and quantum fluctuations give rise to fluctuations about the smooth, uniform expansion. There are quantum fluctuations on top of that, an analog of Hawking radiation in the early universe. And what it looks like, these virtual particles, when you see the imprint that they would leave on the fields in empty space during inflation, is you would see something like this, a random field of variations in the density in the vacuum state. And if that looks familiar, well, it might look a bit like this. That's the statistics of quantum vacuum fluctuations are exactly the sort of fluctuations that we see in the light from the cosmic microwave background sky. Remember, the most distant radiation in our universe, from a few 100,000 years after the hot Big Bang, it shows these temperature variations. And our best explanation for why there is variations in the temperature of the microwave background radiation is that they actually come from quantum fluctuations, quantum physics during cosmic inflation, a fraction of a second after the Big Bang. Well, I've thrown a lot of information at you there, but I hope that's maybe given you a glimpse into some of the ideas we have about our universe. So I hope I convinced you that the universe is big, really big. We can look out billions of years into the past of our universe, and what we see, even on those largest scales in our universe, is we see structures. And ultimately, the fact there's structure in our universe, even at the very earliest times, it's from those structures that all the subsequent structures, the galaxies, the stars, and ultimately the people in our universe come from the fact that even in the very early universe, the very distant universe, there is structure. And all of that can come from this process of inflation. Nothing, I called it before. It's empty space, but it's empty space, the energy, very high energies of empty space in the very early universe, driving a rapid expansion, producing quantum fluctuations from which the large-scale structure of our universe forms, and which we can maybe see. And indeed, now cosmologists are studying the nature of structure in our universe at the earliest times, in the hope that we can, by studying those fluctuations, we can reveal the physics of cosmic inflation, the physics at the edge of our observable universe. So I hope I've given you some food for thought there. I will finish at that point, but I think we will have time for questions if people would like to enter questions in the chat on the YouTube channel there. We will have those passed on to us.
So first things first, of course, a big virtual round of applause, David, for giving such a wonderful presentation. We can't hear you clapping out there, but I'm sure everybody is. So we do indeed have some really wonderful questions, and I'm going to read out the first one of those for you. So the first question is one that was submitted prior to the talk via our Google Forms. And it's a bit of a doozy, but I think you'll have fun answering it. The question from Chris in Petersfield is, if I could stand at the edge of the universe and take a step, what would I be stepping into?
Right. Great question. It is fascinating to think, always to think, if for instance, one way of, as you've seen, I've talked about the edge as somehow being as far as light can travel to us. If we imagine the edge therefore being the beginning of the universe, taking a step back beyond that would have to be perhaps going beyond the Big Bang itself. And the Big Bang we think of as being actually being the beginning, not just of time, but therefore of space as well. So in the traditional view of the Big Bang, there is, that you just can't step back. There really isn't, not because there's something that it's really, you can't step back because there is no space there. There's not even any time there before the Big Bang. Some people have speculated that this idea of inflation could give you be sort of an extended view of the universe, something that it could almost be replace the Big Bang. Now that's really is not proven, but it's tempting to speculate. So maybe as you step beyond our observable hot Big Bang, perhaps you're stepping back into that inflationary era. So perhaps you'd be in an inflating space, but it expands very rapidly. I think you might get shredded apart by that rapid expansion of space. So best to stay in the present, I think.
So I thought you'd enjoy answering that one. So for the next question, so this was submitted to the chat window during your talk. It's from Jacob, who's a sixth form student in Portsmouth. So Jacob's wondering how difficult it is to enter the field of cosmology and astrophysics. And they're asking because it's actually something that they're thinking about maybe pursuing in the future as a possible career path.
Yeah, so it's a fascinating subject to get into, so I'd encourage you to indeed to find out more about it. The way to get into that is through studying science, and really physics is the science that we use to describe, for instance, the expansion of space-time, a theory like general relativity. That's one of the fundamental theories of physics. So but physicists, especially theoretical physicists like me, use the language of mathematics. So we're studying physics and mathematics, and you could potentially study either of those at university. A university degree gives you the knowledge, the basics to really tackle some of these kind of fundamental physics problems that I'm talking about. And that's what I did many years ago. I did a physics degree, and then I went on and did a PhD. And so if you're really interested in studying it beyond a degree level, you can go and to become a researcher. The sort of apprenticeship for researchers is a PhD. And it's challenging, but if you're really interested in it, I encourage you to do that. And look at university degrees that include astronomy, astrophysics, and cosmology. In the UK, we're lucky to have a great variety of universities, lots of different specialities. In Portsmouth, we've got an Institute of Cosmology and Gravitation, but there are specialist institutes, and those people working in those institutes will be teaching on physics and mathematics courses and astrophysics courses for undergraduates.
So, David, just to build on that question a little bit, would you agree that we're starting to see people coming into astronomy from, I guess, slightly less traditional backgrounds, so things like computer science, data science, even things like psychology and biology?
Yeah, it's on my as a theorist, I kind of I'm on the more mathematical side of physics, and so there's a strong emphasis on the physics and the mathematics. People can come in traditionally from either of those routes, and certainly computer science these days is, or more broadly, data science. Is having a huge impact on all the sciences. One of my PhD students who worked with me recently had done a computer science as his first degree. I think he then did a master's in astronomy. And then came in to do a PhD in cosmology with us in Portsmouth, and ended up going off into work at Imperial College in the epidemiology department, because he found the mathematical modeling he was doing in the universe he could apply to epidemics, which turns out to be very topical. So there's a range. There's a range of different skills, and certainly the data science and computing has become very valuable. And indeed, conversely, a lot of astronomers, actually end up going into data science and applying these techniques that we use to observe the most distant objects in the universe, for instance. A lot of those techniques are now in Portsmouth. We're using them indeed to help people understand COVID and how you spread COVID, and there's all sorts of epidemiological or different biological and societal implications and applications of data science.
So I think now we'll jump back to a slightly more theoretical question. So this is another fun one from Alex. So the question is, why did gases randomly clump together to form planets, nebulae, etc., if matter is meant to be spread evenly?
Yeah, so that's a good question, because the universe starts off very even, very smooth from what we see in so I keep going back to that cosmic microwave background radiation, but it's the earliest light we can see, and it is almost exactly 3 degrees. And the universe at those early times is expanding very uniformly. And it's true, if it was perfectly uniform, it would always expand uniformly. And we think you need these quantum fluctuations and we think the best guess is maybe inflation, but that's our best model at the moment. But something has to form a slightly denser region here and a lighter region here, and then a denser region here. And then what happens, and it's only the very slight fluctuations, but it's gravity. So it's gravity that makes matter clump together. So even if it starts uniform, if you have slight fluctuations and you allow 14 billion years, you can actually form the gases under their own weight, can come together, condense to form, well, stars. And after the life cycle of stars, you can maybe produce heavy metals that can form planets and planetesimals. And but it all starts, we think, from those what we think are quantum fluctuations, tiny fluctuations, but over time with gravity they collapse under gravity and form stars and planets and people and everything we see. Yeah.
So another question. So from somebody with the screen name Starship Earth, and by the way, that's a fantastic name. They're asking, is there a point where the universe is so large and I guess expanding so quickly that light is moving too slowly to reach us?
Yeah, so that's a fascinating thought, isn't it? That's right. So we think that's exactly the sort of thing that would happen if you were back in that first fraction of a second during cosmic inflation. There would indeed be a very rapid expansion, so that unless you were within a small distance, and really it'd be within a microscopic distance of other it's only within a tiny region that you see light, because the universe is expanding so quickly that light that's further than a millimeter away, say, would be the expansion of space would actually be faster than light could get to you through the expanding space. And that actually, technically, mathematically, that causes an event horizon in an inflating universe. And in the very early universe, that could be very small, and so it's quite a dramatic. It's a really dramatic effect. That's inflation. But we actually seem to see something like that in our universe today, but it's a much more low energy, leisurely, slow expansion. And yet, if you really have dark energy in the universe today, eventually, at distances approaching 14 billion light years away, by that point, actually, that slow expansion, but over such a large distance, would actually stop light traveling to us, because as light tried to travel to us from such large distances, that expansion of space, albeit slowly, but over such great distances, would stop light getting to us. So yes, we think there is probably an event horizon around us in the universe today. There's a limit to how much further we will ever see into the universe because of that, in the presence of dark energy in the universe today. But it's a huge scale, so we don't see. If you hung around for another 50 billion years, maybe we might begin to see that effect, that the universe would start emptying out. We wouldn't get to see beyond a certain distance.
That's a fantastic answer to a very abstract question. So the next question comes from Aliona. She's wondering whether there are any particular books or resources that you might recommend for studying cosmology and the kinds of things that you've covered in your presentation.
Oh, yes, great question. So there's, I guess, the answer I gave. There's the textbook answer. Literally, is study physics, study maths, and you can really learn about the processes at work. But there are many fascinating sort of descriptions, which can give you at least a glimpse of the ideas at work here. I mean, I studied for my PhD. I studied with Professor John Barrow, who was at Sussex University in those days, and latterly at Cambridge University. And John Barrow has, if you've read any of his books, they're a fantastic description of physics and ideas in physics and mathematics. And I remember reading The Left Hand of Creation by Barrow and Silk. But there are some, many great books written by people like John Barrow. Brian Greene, I think, writes great books. And these days you can find lectures. These are, in fact, both Brian Greene, John Barrow, fantastic lectures you can find on YouTube. So have a look at them. There's, of course, a lot of resources these days. Places like NASA have a fantastic website with fantastic images from the satellite telescopes, and they'll tell you about the science behind that as well.
Okay, thank you, David.
Almost tempted to ask you, Nick, actually, if you recommending that.
I'm trying to think of something off the top of my head, and I'm failing, unfortunately. I've got stage fright.
There are lots of resources out there. I mean, NASA do put a lot of money into science communication, and their website has fantastic images, of course, from the Hubble Space Telescope, but the other telescopes, satellite experiments they're involved in, and there's a lot of science behind that too.
Absolutely. I know there are also, so recently there have been some relatively easy to digest, I guess, books that have come out that have sort of tackled the biggest questions in modern astronomy as well. So worth looking for those as well, because they're quite a good read. Okay, so we are coming towards the end of our allotted hour, but we have time for just a couple more questions. So from Ellie Stiles, and I think, David, you covered some of this in your presentation, but Ellie is wondering, do you believe in multiverses, and how do you think the universe will end? And do people still throw around phrases like the big crunch or the big rip?
Yes, people certainly do discuss the big crunch and the big rip. That's a lot of people working on the nature of dark energy, for instance. So the future of that, because this is really considered, these are ideas about the future of our universe. So there certainly was something very much like a Big Bang in the past. And so it's tempting to speculate as to whether, we might all end up if the universe is expanding now, will it contract in the future? And that's what people call a big crunch. At the moment, the indications are quite the opposite, that in fact there's the discovery of dark energy implies that the universe is going to keep expanding. And in fact, as I was saying, you end up with this large universe expanding forever, empty. It could be a rather dull, empty, cold universe in the future. We're talking about 50, hundreds of billions of years into the future. But it has made some people speculate as to whether dark energy could be more dynamical, and a big rip would require a sort of runaway expansion where it would even end in a singularity. That seems unlikely from what we understand about physics at the moment, but it's always tempting to see, and it's the sort of thing, in principle, astronomers are trying to measure actually the expansion of the universe and how it varies in time. So, it might be we could actually see whether it's speeding up in the way that might lead to a big rip. So astronomers are kind of interested in measuring these things, even though we think it's unlikely, but we thought probably dark energy was unlikely. The multiverse is a whole other discussion. It's really about the effect of these quantum fluctuations, whether they could take over even in at very high energies in the very early universe. And well, at least that's one in the multiverse. Is kind of the idea that there's much more to the universe than simply the observable universe. And indeed, one idea there is that inflation does imply that the universe is likely to be much bigger than simply the patch of the universe that we see. So perhaps I should restrict myself. There's a lot we could speculate about that, but I think at some level it's very likely that there is far more space out there. Not only is the space that we see big, but the space that we don't see is probably even bigger. And if that's what we mean by the multiverse, I think that's very likely.
I think that was a pretty good answer to a relatively complicated question, David. So we are coming towards the end of our session. We have time for one more question. I'm just going to try and choose one that I think you'll enjoy answering. So somebody's asked basically whether it's possible for things to get cooler than absolute zero. So obviously we talk about things tending to 0 Kelvin, so the cosmic microwave background, sort of approaching that as it cools down. Is it possible to actually get cooler than that, David?
Not really, no. So in the sense that I've described it, I think of it as a thermal temperature, and for instance, the cosmic microwave background, as you say, is this weak radiation that is only 3 degrees above absolute zero. And as the universe expands and grows older and expands, the temperature will go down, but it will only ever reach zero. There are some systems that physicists can create that have properties like negative, you could interpret as negative temperature, but I think it's correct to say they're not really, they're not really below a zero temperature. They've not got less energy than a zero temperature in our universe. So yeah, absolute zero is an absolute.
So David, thank you so much for answering so many of the weird and wonderful questions that we've received throughout this session. So there are quite a few that we haven't had the time to get around to. Hopefully we'll look at ways that we can maybe answer a few more of those questions in the coming days and weeks. And of course, if you've attended this talk, we'll let you know if we manage to do that. I'm sure you'll all join me in saying a really big thank you to David for giving such a wonderful talk and for answering so many questions in such a wonderful way. Just a reminder that, of course, as part of this week-long series of events that are being run as part of virtual Pompey Stargazing 2021, there are still things happening tomorrow, on Saturday and on Sunday. So if you haven't signed up for any of those events and you still want to, the details for those for signing up for those should be included in the description for this event. But until we see you again, thank you so much for tuning in tonight to listen, and good night from me.
And good night, and thank you for attending from me. Thank you.